Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Stellar Spectra and Stellar Classification 2 from the paper Astronomy and Astrophysics. So students, let us see what we are going to learn in this module. First, we will appreciate that 8 major spectral classes cannot explain all the diverse stellar spectra. More classes and prefixes and suffixes with the existing classes are needed. Second, we will learn that spectral classes, that is Q, P and W, Wolf-Rayet, are added before class O, and classes R, N and S are appended to the Harvard system as offshoots of classes K and M. Thirdly, we will conclude that WR stars, they are very hot stars because they show emission lines of highly ionized atoms. They have strong stellar winds which blow off the upper layers of the stars, revealing in the lower layers the presence of C and N. Next, we will also learn that R and N stars shows bands of carbon molecules such as CH and CN and are called as carbon stars. Next, we will also realize that the stellar classification sequence is actually a sequence in which surface temperature decreases from class O to class M. So let us start with a basic introduction about the module. In the last module, we introduced the spectral classification of stars. We explained the nature of the spectra as that containing mainly the absorption lines. We discussed the variety in the spectra of stars. Even within the variety, it was possible to discern the pattern. So there are stars with a very few lines. On the other hand, there are stars with huge number of lines and molecular bands. So on the basis of increasing complexity in the stellar spectra, Annie Cannon was able to devise a simple classification scheme known as Harvard Stellar Classification System. So there are 7 major classes: O, B, A, F, G, K and M. They were identified on the basis of their spectra. Each major class was subdivided into 10 subclasses. For example, A0 is followed by F0, which in turn followed by F2. So it was pointed out that the stars belonging to the first 3 major classes, that is the classes O, B and A, are called as early type stars, while the stars belonging to the last 4 major classes are referred as the late type stars. So stellar spectra are much more diverse than we have studied so far. We now dwell upon this complexity. Later, following M. Saha, we will attempt to account for the classification scheme. Wolf-Rayet stars. The classes placed before O are Q, P and W, all hot stars showing emission lines. P stands for planetary nebula, believed to be the stage in the evolution of a star just before it becomes a white dwarf star. W stars are Wolf-Rayet stars, named after the two French astronomers who studied them. The Wolf-Rayet stars show in their spectra broad and intense emission lines of ionized carbon, nitrogen, and helium. So this figure shows the spectra of Wolf-Rayet star WR137. And notice that the intention emission lines of ionized carbon, they are very intense. Wolf-Rayet stars are very hot stars and their surface temperature ranges from 30,000 Kelvin to 50,000 Kelvin approximately. These stars are very luminous. The mean absolute magnitude is around -5. They are about 10 times as massive as the Sun. The stars of this mass tends to have very strong stellar winds. These winds blow away as much matter as 10 to the power -4 solar mass per year, leaving behind a thin atmosphere through which we are able to observe the central region of the star. This region is rich in carbon and nitrogen. It appears therefore that the Wolf-Rayet stars are helium-burning stars, second stage after hydrogen burning, producing carbon and nitrogen, whose lines we see in their spectra. The central temperatures may be of the order of 10 to the power 8 Kelvin. Clearly, Wolf-Rayet is a stage in which the evolution of a star lasting a few 100,000 years. Helium burning. So this figure shows that after the hydrogen burning in the core of the star is completed, the temperature rises to 10 to the power 8 Kelvin, and at this temperature, helium burning can commence to supply the energy needed by the star to radiate from the surface. At this temperature, helium burning becomes possible, and helium reactions produce carbon, oxygen, neon, etc. Scheme of prefixes and suffixes to denote the special characteristics of the spectra. An example of a prefix attached to the spectral class of a star is C, which denotes that most of the lines in the star's spectrum have narrow profiles, such as in the star Alpha Cygni. Some of the other prefixes and suffixes used are the following. N denotes wide and diffuse lines. S is used in spectral classes B and A to denote the lines of narrow profiles, but not as narrow as denoted by the prefix C. E denotes the appearance of the emission lines in the classes O to M, where they are not normally expected. The prefix appearing in classes O and B means that the Balmer lines of the hydrogen are in emission. V denotes the variable spectrum and EV denotes the variable emission spectrum. K denotes the presence of H and the K lines of Ca+. P denotes that the spectrum contains peculiarities not normally found in the spectral class, in which the spectrum is classified. In certain stars of class A, for example, the tines of Si2 and Sr2 are exceptionally strong. These stars are designated as AP stars. Complete stellar classification. To the 7 major classes of the Harvard system, 3 more classes are added. So the stars of classes R and N, they are called as carbon stars because they show bands due to C, CH and Cn. These stars do not show bands due to TiO, the prominent feature of M stars. So stars assigned the spectral class S also does not show bands due to TiO. Instead, they show bands of zirconium oxide, lanthanum oxide and YTO. So the 5 stars which are generally long period variable stars, stars Q, P and W, Wolf-Rayet, are placed before O as shown in this figure. W Equale. W Equale is a typical S star. It is a Mira variable star and its magnitude varies between 7.3 and 14.3. The figure is shown over here. It is a red giant star whose radius varies between about 215 to 240 solar radii. At its peak, it is about 30,000 times brighter than the Sun. Let us now discuss the spectral sequence. This spectral sequence shows the spectra class P, 7 major classes of Harvard system, classes that is R, N, S as shown in this figure. P stars are actually planetary nebulae. Examples of the stars of various types are also given. Planetary nebula is a stage in the evolution of a star just before it becomes a white dwarf star. Spectra of S-type stars. These days, the intensity of lines is measured by CCDs, as it was discussed earlier. So this figure shows the spectra of 2 S stars in the visual range. Now students, notice over here that the lines due to zirconium oxide, which is the distinguishing feature of S-type stars. Surface temperature and spectral classification, Saha's theory. We have already noted that spectral sequence from simple to complex spectra is a temperature sequence. So at the top of the sequence, the surface temperature of O stars is so high that most atoms are ionized. The exception is He, He2, which is difficult to ionize a second time. So these stars show only the lines of He2 and there were other few lines. As we progress to lower temperatures, first we encounter the lines of hydrogen, class A, which has high ionization potential, and then ionized metal atoms, classes F, G and K. So at still lower surface temperatures, even metal atoms cannot be ionized, so we have neutral metal atoms. In classes K and M, the surface temperatures are so low that even the molecules cannot be dissociated. So in the spectra of these classes, we have molecular lines in addition to the host of neutral atom lines. M.N. Saha grasped the true meaning of the spectral sequences. He pointed out that the ionization process is like a chemical reaction and is subjected to the same conditions of equilibrium as is a chemical reaction. So, this notion basically leads immediately to relative numbers of atoms in various stages of ionization existing in equilibrium at a given temperature. Since the intensity of an absorption line is proportional to the number of atoms which can absorb radiation corresponding to this line, and this number being a function of temperature, the intensity of various lines is obtained as a function of temperature. This then allows us to understand the spectral classification based on surface temperature of stars. LTE and Boltzmann law of population of excited atomic states. Now consider an assembly of various kinds of non-interacting or weakly interacting particles in statistical equilibrium at a certain temperature T. This implies that the assembly is in thermodynamic equilibrium TE. So TE implies thermal, mechanical and chemical equilibria. However, as we shall discuss later, these conditions are not generally satisfied in stars. The conditions may be very close to TE, and we may assume that TE exists. Such equilibrium is termed as local thermodynamic equilibrium, LTE, which we will discuss it. So students, the number of particles of a given kind in energy range E and E plus dE is given by the usual distribution law, that is dN equal to dG divided by exponential of minus mu minus E by kT minus plus 1. So here dG is the statistical weight or the number of possible quantum states of a single typical particle of the chosen kind between energies E and E plus dE. So for a non-interacting system, the kind assumed here, the quantum states of a particle of the chosen kind can be enumerated as if the particles of other kinds were not present. The negative sign in the denominator of the above equation is for bosons, which is the particles with spin 0 and integral spins, while the plus sign is for fermions, the particles with spins odd multiples of half. and here the quantity mu is the chemical potential, and in the case of fermions, mu by kT equal to eta, which is nothing but the degeneracy parameter. So when eta is greater than 1, then the system is said to be highly degenerate, and when minus eta is very much greater than 1, then the system is non-degenerate. In the non-degenerate case, 1 in the denominator of the above equation may be dropped and the distribution becomes dN equal to dG multiplied by e to the power eta multiplied by e to the power minus e by kT. If the particles are atoms, then dG equal to J equal to 2J plus 1, where J is the total angular momentum of the atom in the energy level of energy E. For hydrogen-like atoms in the quantum state N, this dG equal to 2n square. Now, if the particles are free particles, that is, they are having momentum in the range p and p plus dp, dg equal to gv by h cube multiplied by 4 pi p square dp, where v is the volume in which the particles are confined and g is the statistical weight of the internal states of the particle. So now, for example, the particle has spin s, then g equal to 2s plus 1. If the particles are photons, then g is equal to 2, corresponding to the two states of polarization. If the particles have spins aligned in a certain direction, or if the photons are polarized, then g equal to 1. Now, for the particles per unit volume in the momentum range p and p plus dp, after substituting the values of dg, we get dn equal to g multiplied by 4 pi p square dp by h cube multiplied by e to the power eta multiplied by exponential minus p square by 2m kt, which is the well-known Maxwell distribution law. Now coming back to the equation of the dN, then the ratio of the atoms per unit volume in the jth state of excitation to the unexcited atoms in the same state of ionization, say ith, is given by Nij by Ni1 equal to Gij by Gi1 multiplied by exponential minus chi ij by kt, where chi ij is the excitation potential. And this equation is the Boltzmann law of population of excited atomic states. Fraction of excited atoms. So the total number of atoms in the ith state of ionization is Ni equal to summation over j equal to 1 to infinity, Nij equal to Ni1 divided by Gi1 multiplied by Bi as a function of t, where Bit equal to the summation over Gij multiplied by exponential minus chi ij by kt. This is called as the partition function for the ionization state I. At first sight, it might appear that in this equation will diverge because the excitation potential reaches the limiting value of the ionization potential epsilon I, and Gij are the positive numbers. But as it happens at many places that the divergence is averted. Actually, each term in the sum must be multiplied by the probability of the existence of the corresponding level. So the probability of the existence of very high excitation states is extremely low because the perturbation from the neighboring atoms do not allow the atom to exist in such states. Thus, a cutoff can be applied after a finite number of terms and the divergence is averted. Fortunately, the precise number of terms retained in the sum is not very important, and the partition function in most cases of astrophysical interest is quite insensitive to this number. Actually, under weak conditions of excitation, the first term in the sum dominates and the partition function is virtually equal to the statistical weight of the ground state. This is particularly true for the atoms of hydrogen and helium, which are difficult to excite. So if we decide to express the excitation and ionization potentials in electron volts, then for hydrogen-like atoms we have Chi equal to 13.6 Z square multiplied by N square minus 1 by N square electron volts, where Z is the atomic number of the atom. So using this equation, we get for the hydrogen atoms, that is putting the value of Chi n, log of N1n by N1 equal to 2 log n minus 68,500 by T multiplied by N square minus 1 by N square. So the left hand side figure shows the fraction of excited hydrogen atoms as a function of the energy level. Now notice over here that there is a decrease in the fraction of excited hydrogen atoms with increasing energy level N, and here the temperature was kept fixed at 11,000 Kelvin. Whereas the right hand side figure shows the fraction of excited hydrogen atoms as a function of the surface temperature for energy level N equal to 2. Notice over here that there is a rapid decrease in the fraction of excited hydrogen atoms with decreasing temperature. So students, let us summarize what we have learned in this module. Because of very high diversity in stellar spectra, all spectra cannot be accommodated in the 8 major classes of the Harvard system. Classes Q, P and W, Wolf-Rayet, are added before the class O. Wolf-Rayet stars are very hot stars and contains broad and intense emission lines. The mass of these stars is around 10 molar mass. These stars have very strong winds. It is possible that Wolf-Rayet stars are helium burning stars and represents a stage in the life of a star. There are several suffixes and prefixes which are used to denote the spectral characterization of stars. A few late type stars are distinguished by strong bonds of, or basically the bands of C, CH and Cn, but not of TiO. These stars are classified as R and N stars and are called as carbon stars. There are also stars which shows bands of zirconium oxide, lanthanum oxide and yttrium oxide. These are called as S stars. S stars are generally variable stars with long periods. Now, M.N. Saha pointed out that the spectral sequence from simple to complex is a temperature sequence. So, Boltzmann law of population of excited atomic states was derived, and it is given by Nj by N1 and basically Nij by Ni1 equal to Gij by Gi1 multiplied by exponential minus iota chi ij by kT. The fraction of excited atoms of hydrogen is a function of temperature. So there is a rapid increase in the fraction of excited hydrogen atoms with decreasing temperature. Thank you.